notice that the name of today's lesson has to do with graphing linear equations, and in fact in a preceding lesson we also made some graphs of linear equations, but let's look at a few more of these. And let's start out with an example, such as 2x plus 3y is equal to 6. And what we'd like to do is to consider the graph of this, and probably the best way to do so would be to get this in terms of y is equal to something, okay? So let's then try to have y is equal to something, and an equivalent equation might be something of the pattern what? 3y is equal to, and what can we say here?
2x.
6 minus 2x. Let me write the opposite of 2x, or negative 2x plus 6, if I may. And I think later on in perhaps 2 or 3 lessons it will be obvious as to why I did this. And now, of course, an equivalent sentence is going to be equal to what? What may we say here, Tom?
Y equals
Y is equal to
negative 2/3 x
negative 2/3 x
plus 2.
plus 2. Everyone agree with that? Okay. Now, let's take this equation and come over to our coordinate system. And notice here we have 2x plus 3y is equal to 6. And let's write that equivalent sentence of y then is equal to a negative 2/3 x plus 2. And for the time being, let's select some value for x and then find its corresponding value for y and see where we can go from there. Okay, suppose x say we're equal to 0, and what then must y be equal to? And y must be 2. So here's 0 comma 2 is this point. Let's put on those coordinates 0 comma 2. And let's pick out some numbers such as x is 3, and what then must be the value for y?
0.
3 over 3 is 1, so it's negative 2 plus 2 is 0, so 1, 2, 3, comma 0 must be on our graph, is that right? 3, comma 0. Well, let's go out and say that x is 6, and if x were equal to 6, y must be equal to negative 2. So here's 3, 4, 5, 6, comma negative 2 is this point. This is 6 comma negative 2. And looking at these 3 points, certainly they do look to be, what's the word? Collinear. And let's then make that domain to be over this set of real numbers. And as soon as we do so, that then enables us to make this line. And putting an arrowhead on each side, each end of it indicates that it goes on forever. Now, we have here certainly a linear function, don't we? Let's write down that word again, linear function. And notice now, if we have a point which is on our graph, the ordered pair associated with that point must satisfy that equation. Isn't that right? And conversely, if an ordered pair of numbers satisfies this equation, then the point associated with that ordered pair must lie on that line. Isn't that right? And this is one of our statements, certainly, that we have been making. Let's try to generalize this. And, let's write the pattern of ax plus by is equal to c. And in this case, we, I think, must agree that a and b are not both 0, okay? And we may have one or the other, in fact, to be equal to 0, and we'll still have a linear equation. And the pattern that we have here is what we generally call the general form, or what we refer to as the general form. We're going to be looking at about 3 or 4 different patterns of a linear equation the pattern that we have here we refer to simply as the general form or the general pattern of the equation of a line. Okay? Well, let's come over to our coordinate system again and look at particular examples. For example, here we have the set of all x comma y such that x is equal to 3. Now notice again, we're talking about an ordered pair of real numbers such that x is equal to 3. Now, in terms of our general case of ax plus by equals c, what number is a equal to? In this case that we have here, 1. What number is b equal to? 0. And c, of course, is 3. Well, let's make the graph of this sentence, and just looking at it, what then can one say about its graph? And from what we did in our lesson last time, and Tim?
Well, it'll be a vertical line.
A vertical line at 3. At x equals 3. Is that right? 1, 2, 3. And it will be this vertical line. And let me ask the question, is this a function? Do we have a linear function here? No. And here's an example which illustrates the fact that not every linear equation gives rise to a function. And in this case right here, if the line happens to be vertical, then in fact we know that it is not a function. Okay? However, let's look at this example in which we have, notice the notation is the set of all x comma f of x such that f of x is equal to negative 4. And again, we may think of the f of x notation in terms of y. And what now is the value for a in the example that we have here? A is 0, and the value for b must be 1, and of course the value of c is negative 4. And what then does this graph look like? And just looking at our formula here, Don?
A horizontal line is y equals -4.
All right, it's a horizontal line. It's going to be parallel to the x-axis, passing through negative 4. You say 1, 2, 3, 4, and we'll then draw this line. And the question is this one a function?
Yes.
And certainly it is. What name did we give this function in our last lesson? This was called what? The constant function. This is called a constant function. It's nice to associate some names with these special cases so that any time we refer to them, we use the word constant function, we have some idea of what we mean. All right, let's look at a fourth example. And here we have an equation of the pattern y is equal to x. Now notice if we put it into the ABC pattern, or in the general pattern, the general form, we then would have what? Negative 1 times x plus 1 times y equals 0. And of course, what number then is a equal to? In this case here, a is equal to negative 1, b is equal to 1, and c would then be equal to 0. Now, looking at this equation, it's much easier to think of it in this pattern. What then can we say its graph is going to look like? And Tim?
It will be a diagonal line
It will
between
be
0, 0 and 1, 1.
All right, now let's see. Now let's take some value for x. Of course, if x is 0, y is 0. I think I know what you mean, but let's now try to pin that down. Let's come out, say, to x be, let x be equal to 3. And if x is 3, y must be 3. 1, 2, 3. And I think there you see these 2 points, and the line must pass through it and through them. Now let's then come down here, say, to negative 2. And what then must y be equal to? Negative 2. And I think there you see that these 3 points are collinear. And indeed, our line is going to pass through those points. And it's going to look something like this. Now, this particular function is given a special name. And I don't know if anyone happens to remember that name. And we may, well, let's look at, say, the number 0 with respect to the operation of addition, in which a plus 0 is a, is that right, for every real number a. And then with respect to multiplication, a times 1 is a. And now here we may think in terms of functions. And without going into any great detail at this time, perhaps there's some analogy there. Don, what would you say?
Identity function?
An identity function. That's a good name that we may give it. So let's call this an identity function, in which later on, when we do more with functions and composition of functions, we're going to utilize this one in more detail. Well, let's look at then at another example. And here we have the absolute value of x is equal to 4. And again, notice we're in the plane, we're in the Cartesian plane, in which we're talking about the set of all x comma y such that the absolute value of x is equal to 4. Now, do you think that this function, or whatever this is, do you think this relation is going to be a function? No. And do you think it's linear? Do you think whatever we have here is going to be linear? No. And it's going to have something to do with its absolute value. And just looking at the sentence as given here, who may think of the graph and what it's going to look like, Brenda?
Well, you'll have 2 vertical lines passing through the x-axis at 4 and negative 4.
2 vertical lines passing through the x-axis at 4, 1, 2, 3, 4, and at negative 4. 1, 2, 3, 4, negative 4. And we have these 2 vertical lines, and that will be the graph. Notice it's one graph consisting of these 2 lines of this relation of the absolute value of x is equal to 4. Very good. And the graph will look like that. Well, let's look at a last example here. We have the absolute value of y then is equal to 3. And of course, again, the idea is to make the distinction between something that has the absolute value of x in it, and in this case, something that has the absolute value of y in it. And what then may we say about this graph, Peter?
There'll be two horizontal lines
Two horizontal lines
crossing through the y-axis at 3 and negative.
at 3 and at negative 3, and indicating that these lines are then parallel to the x-axis. Notice if it has y's in it, absolute value of y is equal to 3, it then is going to be lines which are parallel to the x-axis. All right? And you say then that our graph will look like this, and indeed it is. Well, I think that that's all that we need to do for today, so let me give you your homework assignment for next time. This will be